Welcome to Mrs. Lee's Chemistry Academy, where no students are left behind. Today, we're going to talk about gas laws. This is tied to the learning objective from College Board, that the student is able to use kinetic molecular theory and concepts of intermolecular forces to make predictions about the macroscopic properties of gases, including both ideal and non-ideal behaviors. That the student is able to define multiple representations of a sample of matter in the gas phase to accurately represent the effect of changes of properties on the sample. And the student can apply mathematical relationships to determine the variables for ideal gases. So what is atmospheric pressure? It is created by the air molecules colliding with the surface of the container wall and is defined as force per unit area. Now, how do we measure atmospheric pressure? Mr. Torricelli invented the barometer, in which he used a long tubing and he filled it with mercury because mercury's density is very dense, 13.6 grams per cubic centimeter. Then he inverted it upside down and immersed it into a pool of mercury. Now, the gravity is pulling the mercury column down while the air pressure is pushing it up. Finally, the column stays constant at the height of 760 millimeter mercury above the surface, and that's defined as 1 atmospheric pressure or 101.3 kilopascal. To measure the pressure of a gas, we use manometer. How do we do it? Here's a diagram. Here you have a container containing the gas molecules connected to a U-tube, and we put in some mercury inside the U-tube. On one side, it is open to atmospheric air. Now, you look at the left column or left diagram, you see that the column is a little bit taller on the left-hand side by the distance of h. That means air pressure is greater than the gas pressure by the distance of h. And therefore, when we calculate it, it is equal to 760 minus 25 equal to 735 millimeter mercury. Now, on the right diagram, you can see the column is taller on the right arm, meaning the gas is greater in pressure than the air by the distance of h. So when we calculate the gas pressure, we add 25 to 760, which is 785 millimeter mercury for the gas pressure. In dealing with ideal gas behavior, we use the kinetic molecular theory to make some assumptions. One, we assume that gas particles are so small that they are so far apart from each other that they are compressible. Therefore, we take the volume of the container. Two, that the gas particles are in constant random motion. They constantly collide with one another. And with elastic collisions, it means they go away with equal force. And three, they do not exert any intermolecular force on each other, therefore no stickiness. And lastly, that their kinetic energy is directly proportional to the temperature in Kelvin. When we explore the mathematical relationship in ideal gas behavior, we look at 4 variables. 1, pressure, in atmospheric pressure or millimeter mercury or kilopascal. 2, we are concerned about volume in liters. 3, we're concerned about temperature in Kelvin. And finally, the number of moles represented by N. Now let's look at the first gas law, Boyle's law. If we have a certain amount of gas, we hold it at constant temperature. And it occupies volume 1 with pressure 1. Now, if we increase the pressure to pressure 2, that means gas molecules are being pushed closer together. So now they occupy a smaller volume, V2. Therefore, we can conclude that pressure is inversely proportional to volume. Now, if we draw the graph of P versus V, we get a curve going downhill, meaning that at high pressure, the volume is small, but at low pressure, the volume is large. Now we can further plot pressure versus 1 over V to turn the curve into a straight line relationship. So pressure is inversely proportional to volume, and the slope of the line is defined as P times V. Therefore, we have P1 times V1 equal to P2 times V2, which is a constant, or the slope of the straight line, and this is Boyle's law. Practice problem number 1. I have a gas sample occupying 3.8 liters at a pressure of 912 millimeter mercury. What is the new pressure in ATM if the volume is decreased to 1.5 liters? Now we use Boyle's law to solve this problem because we're dealing with pressure and volume only. And plugging the numbers in, we get 2,300 millimeter mercury. But we still have to convert it into atmospheric pressure by using the relationship. 1 ATM is 760 millimeter mercury, and we get 3.0 ATM. Practice problem number 2. Here I have a diagram of two containers connected together. The left side is a larger container having 3 liters of hydrogen at 0.720 ATM pressure, and the right container is smaller, containing 1 liter of nitrogen at 0.198 ATM. What happens to the partial pressure of hydrogen and nitrogen when I open the stop cork? Now remember, now I have a greater volume for the gas molecules to roam around, a total of 4 liters. So definitely the pressure will be decreased because the volume is increased. So I apply Boyle's law to solve the problem, and I find out that the partial pressure of hydrogen now becomes 0.540 ATM, and the partial pressure of nitrogen becomes 0.0495 ATM. Both pressures have been decreased due to a larger volume for the gas molecules to roam around. The next law that we're going to deal with is Charles' law. If we have a certain amount of gas molecules and we heat it up to high temperature, well, the gas molecules now have greater kinetic energy and they will have more collisions and more forceful collisions. That means the pressure will increase. However, we do not allow the pressure to increase, we hold it constant. That means the volume will have to increase. So volume is directly proportional to temperature in Kelvin, which is illustrated by this diagram. As I increase the temperature, the volume increases. Now then I go ahead and plot the volume versus temperature for various gases and extrapolate the straight line until they all come to the same point, which is negative 273 degrees C, which is defined as absolute zero, which is the Kelvin scale, meaning that at that temperature, all gas molecules stop their movement. So if I look at this slope of the straight line, which is V over T, I then come to this Charles' law of V1 over T1 is equal to V2 over T2, which is a constant. Now practice problem number 3 utilizes Charles' law. I have a balloon of 750 milliliter volume at 25 degrees C. Now I cool it down to 2 degrees C. What is the final volume of the balloon? So now I apply Charles' law to solve the problem. But please remember to convert the temperature into Kelvin. A lot of students tend to forget that and do it in degrees C, and that would get you the wrong answer. So volume 2 is 692 milliliter. Gay-Lussac law. If I have a certain sample of gas at constant volume, if I increase the temperature, that means the velocity of the gas particles will increase. They will hit the container walls more often with greater force and greater frequency. Because volume has to be kept the same, that means pressure will have to increase. So pressure is directly proportional to temperature in Kelvin. And if we plot the graph of P versus T, we get a straight line extrapolated to absolute zero. Now, how do we obtain the data in the lab? We take a round metal ball that's connected to a pressure gauge. And in the round metal ball, it traps a number of moles of air molecules. We then put this metal ball into water at 3 different temperatures. At 0 degrees C for ice water, and for 25 degrees C at room temperature, and 100 degrees C for boiling water. Now we have 3 data points to draw the straight line for extrapolation. So we get pressure is directly proportional to temperature. P1 over T1 equals P2 over T2, which is a constant, the slope of the straight line. Practice problem number 4. I have half a mole of gas in 1 liter flask at 27 degrees C, occupying, having a pressure of 98 kilopascal. What will be the new pressure in atm when the gas is cooled to negative 123 degrees C? So using the Gay-Lussac Law, I then convert the 98 kilopascal into 0.97 atm before I plug it into the formula and make sure that my temperature is in Kelvin. And now my P2 is 0.49 atm. Now I'm going to combine the Boyle's law and Charles's law together, which says pressure is inversely proportional to volume. P times V is a constant, which also says volume is directly proportional to temperature. So V over T is a constant. Now I combine it into P1 V1 over T1 is equal to P2 V2 over T2, which is also a constant, which I call the combined gas law. Practice problem number 5. At 30 degrees C, I have 250 milliliter of an ideal gas at a pressure of 740 millimeter mercury. Now, as I cool it down to 0 degrees C and I increase the pressure to 760, what will be the new volume? Now, I like to do this in terms of changing one variable at a time. I really don't like to just plug numbers in the formula. That's no fun. We need to learn the concept. So first, if I increase my pressure from 740 to 760 millimeter mercury, meaning the volume is also decreased by the factor of 740 over 760. So I multiplied that by the factor of 740 over 760, which is less than 1, which will decrease the volume of 250 milliliter. Now I decrease my temperature from 30 to 0 degrees C. I would convert it into Kelvin of 303 Kelvin to 273 Kelvin. Now, as I decrease the temperature, volumes also decrease. So I multiplied that by a factor of 273 over 303, which is a factor less than 1. My final new volume is calculated to be 219 milliliter. Avogadro's law. If I have increased a number of gas molecules in the container at the same temperature, well, these containers, because they will bump into each other more frequently, there will be more collisions, creating greater pressure. But if I do not allow the pressure to increase, then what has to increase? Volume. So illustrated by this diagram, as I put in more moles of molecules into the container, volume increases because pressure is held constant. So volume is directly proportional to number of moles. So we graph volume versus moles, and we have a straight line. The slope of a straight line is represented by V1 over N1 is equal to V2 over N2. Practice problem number 6. I have 4 liters of gas placed into a cylinder with a movable piston. What is the final volume of the gas if I decrease the pressure to 1/3 of the original pressure? Well, as pressure is decreased, volume will be increased by 3 times. So the volume of 4 liters multiplied by 3 will give me 12 liters of new volume. Now, if I double the temperature in Kelvin, as temperature is double, volume will be doubled. Therefore, I take the 12 liters and double it to 24 liters. And if I decrease the number of moles to 1/5 the original number of moles, that means the volume will be decreased by 5 times. So 24 liters divided by 5 will result in 4.8 liters. Now, deriving from Avogadro's hypothesis, we have the law of combining volumes, which says that at a given pressure and temperature, the volume of gases that react with one another are in small whole number ratios. Now, here's a problem utilizing that how many liters of ammonia are required to change 12.8 liters of nitrogen monoxide to nitrogen gas, the other product being water. So first of all, we need to write a balanced equation, which shows that 4 moles of ammonia reacts with 6 moles of nitrogen monoxide to form 5 moles of nitrogen and 6 moles of water. Now we can replace this volume ratio by mole ratio. So we have 12.8 liter times a mole ratio of 4 moles of ammonia to 6 moles of nitrogen monoxide, and we get 8.53 liters of ammonia. The Avogadro hypothesis says that equal volume of gases at the same temperature and pressure contain same number of molecules. Now, if we have a problem, we say we have 1 volume of iodine reacting with 5 volumes of fluorine, diatomic, both of them are, to yield 2 volumes of the product. Let's make use of this mole ratio relationship or the volume relationship to find the formula of the product. As volume is directly proportional to number of moles, we can replace the volume by moles in a balanced equation. So now we have 2 moles of iodine reacting with 5 moles of fluorine to form 2 moles of the product. Therefore, when we write the balanced equation, we then realize the product has to be iodine pentafluoride, 2 moles of IF5. To sum up what we have learned today, 1, we learned what a barometer is and how it is used to measure atmospheric pressure, as opposed to what a manometer is, as it is used to find the pressure of gas molecules. Secondly, we understand the assumptions of kinetic molecular theory, and we used it to explain the ideal gas behavior as illustrated by Boyle's law, Charles's law, Gay-Lussac law, and Avogadro's law. And finally, we examined the mathematical relationship in the 4 variables between pressure and volume, which is inversely proportional, between volume and temperature, directly proportional, between volume and number of moles, directly proportional, and pressure and temperature, which is directly proportional. We examine these mathematical relationships, look at the graphs, and we apply these laws to solve problems mathematically for ideal gas behavior. I hope that you have found the above lesson useful to you. I welcome any comments from you, and I do hope to see you again next time.